All right, so let's talk about determining rate laws from experimental data. This is what you would do in the kinetic lab. I haven't developed that lab yet, but odds are we'll find a simulation where you do something similar. So you get the data, what do you do with it? We'll do an example at the end as well. So I'll have example data, we'll work through it. But what you want to do first is you want to determine the rate orders. You want to find those exponents. And to do that, there's a couple options. You guys love options, I know. So we got, first, second, and third. So we have 3 options. There's actually not a couple, a few options, all right? And so what we can do is, first there's just, everyone loves this one, estimation. If your numbers are real clear cut, you clearly doubled a concentration of a reactant, and then clearly there was no change or a clear doubling of the rate or quadrupling or so on and so forth, then you can figure out, oh, well, if there's no change at 0th order, if I double the concentration and the rate matched that, that's first order. If I double the concentration and my rate quadrupled, it's second order. If it went up by a factor of 8, if it just blew way up, then it is third order. Now, your data doesn't always lend itself to this well. You might not have a clear doubling. Maybe you go up by a factor of 25% or something like that. You don't go up by 100%. You don't double it. Well, you can, do estimation still, or it might be easier to use this formula. You can derive this yourself. Sometimes when I teach class, I run everybody through it just to put them to sleep. But I'll give you a hint. You start with rate 1 divided by rate 2, and then you logarithm it all right? But if you don't care, that's fine. This is the formula. So you know your rates. You know an initial concentration of A, then we change it to a new concentration. We have our initial rate and we have our new rate. And you just solve this guy and you should get something close to an even number like 1 or 0 or 2 or 3, something like that. You might have to round, it might be like 2.8. Oh, well, then it's third order. But that, is a little more precise than estimation. If you're not dealing with clean cut, doubling and tripling, things like that, this is what you can do. Or if you have a lot of data points and you want to analyze them all simultaneously, well, you can plot. You can just make a line here with your experimental data. So you got some points, you put a line to it, and that simultaneously analyzes all of them. And so what you do is you plot log rate on the y-axis, log of concentration on the x-axis, and this is what you would do in the kinetics lab. Like this would be the technique because we'd have a bunch of data points. And then the slope of that line gives us the exponent. So if the slope is about 1, first order. If the slope is like 2, second order, 3, so on and so forth. If you get a flat line, 0, 0th order. So these are our 3 options. So you do that, and then what do you do for like concentration of B? Well, you just take all these A's right here, and you put B's in their place. That's all you gotta do. All right, and you wanna choose data points too where we're only changing concentration of A. All other reactants should remain unchanged, otherwise it gets all convoluted. But we'll deal with that when we have a sample data table up here. We'll talk about it more. So once you know M and N and O and P and Q and R and S and T, however many of those exponents there are, once you get them all solved, once you know all your rate orders, then you can solve for K. And this one is so easy you sometimes forget to do it because there's a lot of work here. And then out of that falls a one-step cherry on top. People forget to put the cherry on top of the sundae sometimes. So don't forget. So if rate is equal to K times, all the other stuff, well, if I just divide rate by all the other stuff, that gets K by itself. And so that's what we do. We know what A is, we know what B is, we know what rate is. We know some data set where they're all known together. We just plug in our numbers and we solve for K, and then bam, you've got your rate law. You know K, you know M and N and however many exponents there are. You know all of them, you know the rate law. You can now calculate the rate at any given combination of concentrations, okay? So you gotta find the exponents first because you can't find K unless you know what M and N are here. So there is an order to this that you have to do. But it doesn't matter which one you find first between M and N, you just have to find all of them and it doesn't matter where you start. So I'm gonna clear the board. We'll do an example. I'm gonna put up a sample data table and we'll run through here. All right, so clean board. So what we have here is a bunch of sample data, and here's our reaction. So we're saying H2 plus I2 makes 2HI. We've made these measurements. We've measured the rate with these concentration pairs. across the board. They're all at the same temperature. That's key. I forgot to mention that earlier. So you need all your data at the same temperature. If you're changing temperature, you're not going to be able to find the same value for K. So what does this mean? Well, if we look at this, we're going to go, okay, well, our rate is going to be K times concentration of H2 times concentration of I2, oops, H2 to the M, we'll say I2 to the N. All right, so we got to figure out what M and N are, but then we got to figure out what K is. So, you know, our H2 rate order, which I'm calling M, well, how are we going to do this? We've got this data, right? We have to choose our points very carefully here. So if I want to see what happens when I change concentration of H2, I need 2 data points that have different concentrations in H2. That's kind of key, right? I don't want the same number twice for H2 if that's what I'm looking at. But I do want to make sure that I have the same number for I2, because I don't want to change both of them at the same time. So I don't want to do trial 1 and pair it with trial 2 because I'm changing H2 and I'm changing I2, which means that I am changing this equation here and here when I only want it to fluctuate right here and then have everything else around it be unchanged, be constant around it. So I don't want to pair 1 with 2. All right, so I want to find 2 data points where I2 remains unchanged. And so that looks like, oops, wrong color, sorry. Looks like I want to pair trial 1 and trial 3. Okay, and then H2, it changes. All right. So we'll make a little note here, make sure this is clear. So we are going to use trial 1 and 3, okay? Because, again, we're changing H2, but we are not changing I2. I can't use any other data set for this because anything else I put together has different values for I2. So I have to use those. Now when I'm solving for I2, I need H2 to remain unchanged, so it looks like I need to use trials 2 and 4 using that same process. So hopefully that's making sense to you. It's a very important idea. So pause and think about it if it's not making sense, because how you attack these data tables is very important. And so I can do any of my 3 options here when I'm looking for what M is. I can estimate it, which is what I'm going to do, because it's pretty clean cut. Or I could use the whole logarithm thing, or I can plot the logarithms against each other. All right, so I'm just going to estimate it. I is unchanged. H2 concentration goes up by a factor of about 5. We quintuple it. Okay? Well, our rate goes from 1.9 times 10 to the minus 23 to 9.3 times 10 to the minus 3. So get 23. So guess what? That went up by a factor of about 5. So concentration of H2, you know, that went up, I don't know how to mark this, went up by a factor of 5, and so did rate. There we go. That means it's first order. So M equals 1. Because essentially what I'm saying is, well, I quintupled in here, and the effect on the right-hand side, I multiplied the right by, you know, this piece by 5, this piece multiplied by 5, first order. All right, so M equals 1. All right, this is the estimation technique. You can double check me if you want. You can plug this into the logarithms. You can make plots. You don't have to do exactly what I did here. You can try the other techniques out with it. But I'm telling you, it's first order with respect to H2. I've never written anything wrong on this board. Don't look at the molecular orbitals video again, and who knows what else we'll find between now and the week where you just did that. All right, so what do we got to do next? We got to find the I2 rate order, N. This guy's like, I2 have a rate order. Okay, don't forget me. So we need to analyze 2 and 4. And again, I'm going to estimate. H2 is unchanged. I about double concentration, a little under double the concentration, and I about double my rate. I go from 1.1 to 1.9. They're both times 10 power negative 22. All right, so concentration of I2 is doubled, and my rate is doubled, approximately. Like I said, I'm estimating, all right? And so what does that mean? Again, it's first order, okay? So, both of these are first order, nothing, you know, moved up by a factor greater than what we multiplied by. So for example, if we had looked at 2 and 4, I about double the concentration, but this would be about 4 times. So if this was like about 4 times 10 to the minus 22, then it would have been second order. If it was about 8 times 10 to the minus 22, it'd be third order. If it was unchanged, it was about 1.1, then it would be 0th order. But it matched, so it's first order. So I'm just estimating. Like I said, I encourage you, use the logarithm formulas, make sure that those are working. Who knows, maybe I've overestimated. You can always double check me. All right, so n is also 1. All right, so next we just find k. And I can pick any of these data points, all right? And I'm just gonna go, I don't like to read down the list. I'm gonna go data point number 1, okay? And so here's what I know right now. Rate equals k times H2 times concentration of I2. All right, that's what I know. I don't know k. All my rates I know for these specific situations. I don't know universally. All right, but if I solve this for k, it'll just be rate over concentration of H2 over concentration of, or times concentration of I2. Well, look at that. I can do a rate with a concentration with a concentration, rate, concentration. I can't miss. And so again, if you had this in Excel, you can plot a line, you can get a nice statistical average. I'm just gonna pick one data point as an example here because my whiteboard doesn't have Excel installed on it, all right? So I'm gonna pick the first data point because I'm too lazy to even read the second line, all right? Too long, didn't read, okay. So K is equal to 1.9 times 10 to the minus 22 molarity per second divided by concentration of H2, which is 0.0113 molar times concentration of I2, which is 0.0011 molar. All right, so I just plug all my numbers in, and then I solve, and I get 1.5 times 10 to the minus 18. All right, and then what are my units going to be? Well, this is going to be per molarity squared second. All right, because I've got, whoops, not molarity squared, just molarity. Per molarity second. All right, looked at the wrong line in my notes. Because I'll have molarity cancel with molarity. I got 1 left over per second, so that's the way it works out. Or you can write it, you know, molarity to the -1, S to the -1, so on and so forth. Number of ways you can represent it. But in this situation, this is an overall second order, because first and first, it's an overall second order because we just add up all our rate orders. M plus N equals 2. It's overall second order if our reaction is overall second order. These are the units we get for K. So all overall second order reactions will have the same units for K, because when we multiply this bad boy out, like we have it here, we'll get molarity per second. That's what K does. Gets us molarity per second and it dials it in. Now, you can always check your result. You can plug in the numbers for H2 and I2 here, plug them in with K and everything, and see if you get, you know, this rate plus or minus a small rounding error. That's one way you can check your result. There's a number of things you could do here. Or you could calculate the rate at a new set of concentrations. Like what if H2 was 1 molar and I2 was 1 molar? What would our rate be? Well, it would be a lot more, let me tell you. But you could actually calculate that and solve once you know K and your rate orders. So we know the whole rate law. So, you know, rate law is a lot like bird law. The only way you get to know it is when you practice it. So you gotta practice, practice, practice. You wanna know bird law, you gotta open a bird law practice. That's the way that works. Be a bird attorney. Rate law, you gotta do practice problems. So you're not gonna see me do this one time and get it. This is intricate. Even just this first step can really trip you up. So you wanna make sure you're putting practice in. So I'll have a worksheet with at least 1 or 2 of these on it for you to practice, but also SmartWorks gonna be full of stuff, your book's full of stuff. We're gonna have a lab where you practice it. Like, this is a key idea of this chapter, being able to determine these rate laws. How is concentration going to affect the speed that this reaction progresses at? Okay. So next we're gonna talk about integrated rate laws. And those have to do with how our rate is changing with time. So we just talked about how rate is changing with concentration. Next we're gonna talk about time, and after that, temperature. And then we're pretty much done with the chapter. So concentration, temperature, and time. How all of those affect our rate are kind of the key ideas of this chapter, as well as what a rate is. So hopefully these ideas are starting to click. But if not, like I said, just practice, practice, practice.